previous video we had already discussed about image segmentation and the first order derivative and second order derivative. So now the second order derivative, that is the Laplacian, is of 2D function f of x comma y. So Laplacian or del square f is equivalent to del square f by del x square plus del square f by del y square. So as we have already discussed about Laplacian equation, which is del square f is equal to f of x comma y minus 1 plus f of x comma y plus 1 plus of f of x plus 1 comma y plus f of x minus 1 comma y minus 4 times of f of x comma y. So this mass satisfies that equation. So this mass is corresponding to a Laplacian operator. And if we are going to consider the diagonal values also or diagonal pixels also, then this mask is corresponding to a diagonal Laplacian. As you know that Laplacian or second order derivative is an independent of direction. So Laplacian is also an isotropic or rotation invariant. Now these are the 4 different masks corresponding to Laplacian operator. So we can find out that we are moving from darker pixel to a lighter pixel with the help of second order derivative, or from a lighter pixel to a darker pixel. So if we are moving from a darker pixel to a lighter pixel, then the sign will change from minus to plus, and from lighter to darker it will change from plus to minus. So these can be found out with the help of these 2 masks. So if we the center element is minus 4, then all the other 4 elements which are neighboring pixel n4 will be represented by 1. If the center element is positive, then the n4 pixel are represented by minus 4. If we are also considering the diagonal neighbors, so now n8, so here the center element is minus 8 and the rest of the elements are plus 1. And if the center elements is positive 8 plus 8, then the rest of elements are minus 1. So with the help of this mask, you can find out the edges information, or you can find out. So with the help of these masks, you can find out the isolated points. So now, as you know that local changes in intensity can be detected using derivatives. So we know that the point detection should be based on the second derivative, as it has a stronger response at the isolated points. So this one is corresponding to a Laplacian kernel. Now we are going to run this Laplacian kernel over an input image. So f of x comma y is going to be convolved with this Laplacian kernel. And finally we are going to get a processed image that is denoted by r of x comma y. So if we are going to put some kind of thresholding condition, then the output image g of x comma y is equal to 1 if absolute value of r of x comma y is greater than t, else it is 0. Now you can see in this figure A representing the Laplacian kernel and figure B represent an X-ray image of turbine blade with a porosity manifested by a single black pixel. And C results when we are convolving this Laplacian operator with this input image, which is denoted by r of x comma y. And if we have applied certain kind of thresholding condition where t is equal to 90% of the highest absolute pixel value, then we are going to get an isolated point. Now next one is a line detection. So based on our previous discussion, we know that for the line detection, second order derivative results a stronger filter response and to produce a thinner line as compared to the first order derivative. For example, you can see here on a ramp, for a ramp function, the first order derivative is a thicker as compared to the second order derivative. So this figure A is a wire bond electronic circuit, and when we are going to convolve it with a Laplacian mask with the diagonal elements also, so we are going to get a figure number B. And here this circle shows the magnified view, and the mid gray level ranges are representing a background. The light intensity या shades represent the positive value and the darker intensity shades represent a negative value. Figure C is corresponding to an absolute value of the Laplacian. So now you think that the negative value can be easily handled by taking the absolute value. However, figure C shows that this approach double the thickness line. So a more suitable approach is to take only a positive value of the Laplacian. As we know that the Laplacian is a independent of direction, or is it is isotropic in nature. So when we need to detect a line in a particular direction, then Laplacian is not going to be helpful. So line detection of mass for a specific direction. The preferred direction of each mask is weighted with a larger coefficients, and the coefficient in each mask sum is 0, so it does not have any effect on constant intensity. At a point given in an image, if r of k is greater than r of j, for all j is not equal to k, then the point is said to be associated with a line in a direction of mass k. Suppose that an image with a constant background and containing a various lines oriented at 0 degree, plus minus 45 degree and 90 degree is going to be filtered. So we are going to use a horizontal mask to get a line edges which are in a horizontal direction. So the maximum response would occur at an image location in which a horizontal line passes through this middle row of the kernel. Similarly, for the second kernel, the response to be best to the lines oriented at 45 degree, plus 45 degree. Similarly, for the third kernel, the best response for the vertical lines, and for the third kernel, we are going to get a best response for minus 45 degree. And the preferred direction for each kernel is weighted with a larger coefficient, that is 2. I think there is a mistake here. We have to mention it minus 45 degree and this has to be plus 45 degree. So horizontal mask will result with a maximum response when a line passes through a middle row of the mask with a constant background. The similar idea is used with other masks. Alternatively, if we are interested in detecting all the lines in an image in a direction defined by a given mask, we simply run the mask through the image and threshold the absolute value of the result. The points that are left are the strongest response, which for lines 1 pixel thick correspond closest to the direction defined by the mask. So this again we are taking the same example. So figure A is a binary wire mask bond and figure B represent an absolute value result after processing with a minus 45 line detector. And if we are putting some kind of thresholding value, then this figure is corresponding to that one. Now detection of lines in a specified direction, you can see here this one is corresponding to 45 degrees. So when we are going to convolve this binary image with this mask, so we are the output of that one is represented in figure B, and this one is zoomed version of this area, and this one corresponding to zoom version of this area. And this figure E, when we are setting all the negative value is equal to 0, then we are going to get this figure, and if we are putting a certain kind of thresholding condition, then we are going to get this one. Now edge, a set of connected pixels, the boundary between the two regions with relatively distinct gray level properties. So there is an assumption the regions are sufficiently homogeneous so that the transition between the two regions can be determined on the basis of a gray level discontinuities alone. So edges can be differentiated, or edges model can be classified according to their intensity profile. For example, this one is step edge, which is characterized by a transition between the two intensities levels, occurring ideally over a distance of 1 pixel. While digital images have an edges that are blurred and noisy, with the degree of blurring determined by the principally by the limitation in the focusing mechanism. As you can see here, there is some kind of blurring, so there is a RAM function here. So in such situation, edges are more closely modeled as having an intensity RAM profile, such as the edge shown in this figure. A third type of edge is also called roof edge, and having the characteristic as shown in this figure. So roof edges are models of lines to a region with the base of the edge being determined by the thickness and sharpness of the line. So transition between the two intensity levels occurring over a distance of 1 pixel, then it is represented by step edge. Blurred and noisy edges with a degree of blurring determined by the limitation in the focusing mechanism. The slope of the ramp is inversely proportional to the degree of blurring. As we are going to increase the degree of blurring, the slope of the ramp is going to be increase. No, the slope of the ramp is inversely proportional to the degree of blurring. As we are going to increase the degree of blurring, the slope of the ramp is going to be decrease. Now roof edges, models of lines through a region. The width of a roof edge is determined by the thickness of the line. So now, as you show in the, you can see in the figure that there is a ramp edge. So this figure B is corresponding intensity profile. The figure shows also the first and second derivatives of the intensity profile. So moving from left to right along the intensity profile, we note that the first derivative is a positive at the onset of the ramp and at the points of the ramp, and it is 0 in the area of constant intensity. The second derivative is positive at the beginning of the ramp and negative at the end of the ramp, and 0 at the point on the ramp and 0 at the point of constant intensity. So it is 0 on the point on the ramp and constant intensity. The sign of the derivative would be reversed for an edge that transition from light to dark or from dark to light. The intersection between the zero intensity axis and a line extending between the extrema of second derivative makes a point called zero crossing point of the second derivative. So we can conclude from the observation that the magnitude of the first derivative can be used to detect the presence of an edge at a point in an image. Similarly, the sign of the second derivative can be used to determine whether an edge pixel lies on the dark or on the light side of the edge. So the magnitude of the first derivative is used to detect an edge. The sign of the second derivative can determine whether an edge pixel is on the dark or on the light side of the edge. Now, behavior of first and second derivative of noise images. So this figure, column first A, shows the intensity profile corrupted by a random Gaussian noise of 0, mean and standard deviation of 0, 0.1, 1 and 10. And the second column represents the first derivative of this first column. And this third column gives the second derivative of this first column. So as you can see here, that the second order derivative is much more sensitive for a noise. Now, basic edge detection. Detecting a change in intensity for the purpose of finding edges can be accomplished using first or second order derivative. So now gradient operator. The gradient of an image f of x comma y at location x comma y is defined as vector delta f is equal to gx gy, where gx is del f by del x and gy is del f by del y. So it gives the maximum rate of x of f x comma y per unit distance. So the magnitude of the gradient vector can be defined as delta f. Magnitude of delta f is equal to under root of gx square plus gy square. So now it can be approximate as absolute value of gx plus absolute value of gy. The direction of the gradient vector is defined as alpha x comma y is tan inverse g of y divided by g of x. Now, for example, computing the derivatives in x and y direction using 3 cross 3 mask. So if we are going to convolve a mask in the x direction, we are going to get a gx. If we are going to convolve of mask in the y direction, so we are going to get a gy. And as you know that we can also measure the gradient vector, which is equivalent to tan inverse of gy by gx. And the s direction is perpendicular to the gradient vector. So these are the various masks in the gx and gy direction. So this one is corresponding to Roberts, this is corresponding to Pivot, and this one is corresponding to Sobel. Now the next slide shows the Pivot and Sobel operator mask in a diagonal directions. Now for example, this is an input image. If we are going to take a convolve this image with a Sobel operator in the x direction, so we are going to get a gx. And if we are going to convolve this image with a Sobel mask in the y direction, so we are going to get a gy. And finally the magnitude is equivalent to mod of gx plus mod of gy. But you can see here the contribution made to the image detailed by the wall bricks are significant. So this level of information is often not needed. So what we can do, first we are going to smoothen the image, then again we are going to perform similar operations. So this one gives a mod of gx, this one gives a mod of gy, and then finally we are going to add this mod of gx plus mod of gy. So almost no contribution due to the bricks, dominated by the principal edges. Now if we are again apply the operator in a diagonal direction, so we are going to get a diagonal edge in plus 45 degree and minus 45 degree. So if we are convolving an input image with a Sobel operator mask plus in the plus 45 degree, we are going to get this image. If we are going to convolve an input image with a Sobel operator of minus 45 degree, we are going to get this image. Now combining the gradient with the threshold. So this one here we can see in this figure there are a lot of bricks detail. So we do not need those details. So we are going to put certain kind of thresholding condition that if T is greater than or equal to 33% of the maximum intensity value, then this figure corresponding to threshold after threshold operation. And similarly, if this is an input output image, after we perform gradient before gradient operation, we are taking the smoothen of the image and then perform the gradient operation, and then we are going to put a same thresholding condition, so that is corresponding to this image. Here more finer details of the bricks has been gone. So in the next lecture we are going to discuss about another similarity based technique for image segmentation, that is known as Huff transform.